So I'd like to obviously credit my colleagues who worked on this project. It's across several agencies. I'm going to be talking about techniques to model radiation forces on the GPS-2R spacecraft. Now, okay, a lot of the process of orbit modeling involves calculating forces, developing models of forces on space vehicles. So in this case, I'm going to be talking about photon pressure. So, okay, we all know that equation. That's probably the most famous equation that there is. But a slightly more complete version of it is this. Now, in this equation, this version of it, the rho is the momentum of the particle. M0 is the rest mass. Now, if we're talking about photons, radiation pressure involves photons, then they have a rest mass of 0. It gives us a very nice, simple relationship between momentum, the energy of the photon, and speed of light in vacuum. So the practical implications of this illustrated here. If a photon impinges upon the space vehicle, it transfers that momentum to the body of the space vehicle, gives it a little push. If a photon is then emitted or transmitted by the space vehicle, you get a recoil force according to Newton's laws of motion. So if you can add together all those effects, you'll calculate a resultant force of the photons either impinging upon or being emitted by or being transmitted by the space vehicle. Now, one added complication to that involves this material called MLI, multi-layered insulation, which covers the body of a space vehicle. Now, this is particularly important for the 2R spacecraft. I'll show you why in a few minutes. Now, the main thing, what MLI does is it shields the bus of the spacecraft from the heat in the space environment. So its job is essentially to stop heat getting through to the bus of the space vehicle. And so we developed this equation here, which describes the thermal response of the MLI to the radiation incident upon the surface. So this is the 2R space vehicle. There are a couple of variants to it, though they have some different structural characteristics. But this is broadly what it looks like. As you see, it's a fairly complicated spacecraft, and the bus is covered in this blackened MLI, which creates a very strong thermal signature on the spacecraft, which I'll show you later. So as part of our modeling process, we build a detailed CAD model of the spacecraft. This is our model for the Block 2A space vehicle. Then we create a database of the optical and thermal properties, and we list which materials are present, and we represent the geometry of the spacecraft in particular ways. We do all this modeling in the body frame of the space vehicle. We then simulate our photon flux using a pixel array. And for each one of those pixels, we sort of project rays of radiation towards the spacecraft, use ray tracing algorithms, which we've developed ourselves, to work out which parts get hit by those rays of radiation. At each one of those intersection points on the space vehicle surface, we look up the material properties. We use a physical model of the interaction of it's all right. We use a physical model of the interaction of the radiation with the actual material properties of the space vehicle. We then calculate the normals at each one of those intersection points, and we work out if the radiation bounces off in a particular way, and we work out, does it intersect anything else? We call those secondary intersections. Then we sum together all those all those force vectors, which we get out of that computation, and calculate a resultant force on the space vehicle. And that force is varying as a function of the orientation of the radiation source in the body frame of the space vehicle. We then flip those pixel arrays around the space vehicle bus, project the rays towards the space vehicle, work out which bits get hit, look up the material properties, do the force modeling, calculate the normals, work out where the radiation goes afterwards, and so on, carry out the computation. So we then flip these pixel arrays around the space vehicle in multiple places using what we call a spiral points algorithm. So put the pixel array there, work out the force. Put the pixel array here, work out the force. Put the pixel array there, work out the force, and so on. So we do these computations a priori using large, powerful computers. Typically, we'll have 10,000 spiral points, and we'll do the pixel array resolution modeling at a 1 millimeter resolution. So that gives us a sort of, you could say that would give us a lookup table of the the forcing on the space vehicle due to a radiation source of a particular energy in the body frame of the space vehicle. What we do to make this run fast when people are actually doing implementations of these models in orbit determination is we fit a continuous function to that data. And in the last couple of years, we've done work on automation of that process, and we've done work on trying to make the thing much more numerically stable. There are some numerical aspects of fitting a function to a forcing function on a sphere. So we tried to numerically stabilize that algorithm and have ways of optimizing the process. So this is described. I'm not going to go through this now. You really will fall asleep. But there's a technical paper about that coming out soon. The question is, these techniques, how well do they work? At UCL, with our main contribution to the IGS is to try to develop physical models of these interactions of radiation with space vehicles. So this is a simple example of what gives us confidence that these ideas work. So what we're going to do is we're going to take some initial conditions of a space vehicle, position and velocity, and then we're going to predict forward from there. Do a bit of fitting for the first 3 hours prior to this to tune the initial conditions, but then predict forwards in time and compare the predicted trajectory to a precise orbit, and then look at the along track error in that. So if we model gravity, third body effects, general relativity, tidal forces on the Earth, those kind of things, and we include a solar radiation pressure model, after about 12 hours, you have about 8 meters of orbit error. That's just for solar radiation pressure only. Now, for the 2R spacecraft, if we then add in the thermal effect on that blackened MLI, then you see a dramatic improvement in your ability to predict the orbit. And that shows us that the thermal signature on these satellites is very strong. If we then add in the antenna thrust effect, we get we get better prediction, and then add in Earth radiation forcing, you get a very nice prediction of satellites. So actually, our group at UCL was the first ones to demonstrate the importance of antenna thrust and Earth radiation forcing in these problems. So the experiment we've conducted here, which primarily experimental part's been done by Tim Springer, we did the analysis in Napios. It has a 100-station network. We took 1 year of daily orbits for all the 2R spacecraft, and then we looked at looked at the empirical parameters, and I'll show you the parameterization in a second, and looked at the overlaps as metrics of quality of the process. So, force model parameters. The first part is just the conventional econ model, which of course has been long used in the IGS and proved to be very effective for many years. This is, of course, a completely empirical model. That means that a priori, you aren't guessing anything about the space vehicle apart from perhaps the axes along which these forces are acting. And probably the most important one for us here is that D0 parameter, and that's just trying to pick up empirically the force between from the sun towards the space vehicle. Then in the second case, we used ecom plus a box and wing model. So all of the empirical ecom parameters plus the box and wing model. And then in the final test, we used the bus model from the UCL grid file approach, and then plus the empirical parameters as well. So the question is, how well did all this work? Okay, so this slide is showing you the over 1 year the average of the D0 parameter. So on the first part here, we would expect what we see there. This big blue part here, that's the D0 parameter. It's about 1 × 10⁻⁻⁷ meters per second squared as an acceleration. And of course it should be large because this empirical parameter is trying to absorb all the forcing from the sun towards the space vehicle. Now, when we apply the box and wing model plus the econ parameter, we would expect that to reduce because the box and wing model should be picking up some of that physical effect a priori. And again, this is what we would expect as well, because the UCL model attempts to model many of those forces physically, directly, then we would expect that empirical parameter to go down. Now, what this is telling us is that as you go from the left to the right, you are modeling more and more of the physics of the process, and that process is being done effectively. If the empirical parameters were growing as we went to the right, it would indicate we were somehow getting the physics of this problem wrong at some level. It's not zero for the UCL model, and that's probably because we're not modeling the thermal gradient force on the solar panels in this test. I wouldn't expect that to go to zero. Then we've got some orbit overlaps. So the orbit overlaps, so there's one common point between today and tomorrow's orbit, and that occurs at midnight. So because each day is computed independently, when you compare the position of the satellite at the end of one day with the position of the satellite at the beginning of the following day, then if those are consistent with each other, it shows you that your modeling is effective. Because there can be many things can map into overlap error. It could be frame transformation errors. There could be lots of things that would affect it. But what we found is that consistently, as we go from the ecom-only model to the box and wing, and then down to the UCL model, that the 3D is improving. Finally, this is radial cross-track and long-track broken down and 3D. And again, what we see is consistently you go from the empirical model to the box and wing model to the reasonably good physical model that we've developed, and you see a consistent improvements in the overlaps. And that means that the precision of the orbital process is improving consistently. Now, this is actually the first time a test like this has been done in the IGS of this kind. So if I conclude, so this grid file approach we use at UCL has been tested before by JPL and by Goddard on low Earth orbiters. So we have confidence in it as a computational process, but it's never been done in a sort of a large-scale IGS test like this before. The tests show that we get orbit modeling improvements, both in the accuracy of the physical modeling and in the orbit overlaps. So we're not done by a long chalk in testing here. These are just 2 tests with 1 year of data.